Drug addiction is a major illness that is particularly mediated by the Mesolimbic reward system. Natural rewards, such as food or sex, as well as synthetic drugs, act as reinforcers that are responsible for the activation of this system, causing there to be an increase in extracellular concentrations of the neurotransmitter dopamine. Structures in this pathway include the ventral tegmental area in the midbrain and the nucleus accumbens in the basal ganglia. The ventral tegmental area synthesizes dopamine and its neurons project to the nucleus accumbens. This pathway influences the hippocampus, amygdala, and prefrontal cortex in memory, emotion, and decision-making, respectively. Opioids are a type of drug that target this mesolimbic reward pathway. There are two classes of this drug. There's naturally occurring opioids and there's synthetic opioids. Endorphins, which are found in the brain, are naturally occurring. Synthetic opioids are derived from the opium plant and mimic endorphins' euphoric effect. Heroin, one of the most potent synthetic opioids, is the focus of our discussion today. Heroin is known to induce sedation and cause pain relief. Heroin is medically prescribed in the United Kingdom, Switzerland, the Netherlands, Denmark, and Germany. However, in the United States, it is often abused as a recreational drug. It is synthesized from morphine, which is an endogenous opioid. Heroin is an ester molecule consisting of two acetyl groups added to morphine. It has a high lipid solubility, allowing it to cross the blood-brain barrier faster. Opioid receptors are distributed in the brain and spinal cord, with the limbic areas having the highest concentration of opioid receptors. Mu, kappa, delta, and nociceptin opioid receptors represent the originally classified receptor subtypes. These receptors are located on GABAergic interneurons in the ventral tegmental area. All four receptors are G-protein coupled receptors and are important for playing a role in signaling cascades in the GABA interneuron by activating inhibitory G proteins. First, heroin binds to the opioid receptor on a GABAergic interneuron in the ventral tegmental area. This causes the dissociation of G-alpha and G-beta gamma subunits from the receptor. The G-alpha subunit in this case is inhibitory and it binds to the effector protein adenylyl cyclase. This decreases cyclic adenosine monophosphate, also known as CAMP, production. In addition, G-beta gamma subunits bind to L-type channel blockers, decreasing the calcium concentration of the cell. With decreased CAMP concentrations and decreased calcium concentrations, we have an overall hyperpolarized GABAergic interneuron. This prevents synaptic vesicles from fusing and releasing GABA. Usually, GABA inhibits the production and release of dopamine in the ventral tegmental area. However, with the decrease in concentration of GABA, this inhibitory effect is removed, thus resulting in an increase in the dopamine concentration of the nucleus accumbens. It's important to understand that it's not dopamine that causes a feeling of euphoria upon the release of an endogenous opioid or the ingestion of a synthetic opioid in the central nervous system, but rather it's the binding of opioids to their G-protein coupled receptors that prevents the release of pain messages, causing a pleasurable sensation or rush. Research in the field of addiction medicine has also recently turned its focus to long-term potentiation, which is believed to modulate learning and memory. Long-term potentiation's role in drug addiction underlies the assumption that drug addiction is a form of learning. Addiction is a complex neurobehavioral phenomenon involving various parts of the brain, including the mesolimbic system. Studies have demonstrated that the ventral tegmental area and nucleus accumbens synapses are capable of undergoing long-term potentiation. After an increase in the stimulation of a neuron, the firing of its postsynaptic neuron increases significantly. The stimulus causes the neuron to depolarize, and in the presence of glutamate and depolarization caused by the entry of sodium ions through the AMPA receptors, the magnesium block of the NMDA receptor is removed, and this causes the opening of calcium channels. These calcium ions have several effects within the cell, one of which is to activate the calcium calmodulin dependent protein kinase. These kinases activate AMPA receptors and increase the calcium conductance of NMDA receptors by phosphorylation. Thus, when the neuron fires again, the response of the postsynaptic neuron is potentiated. After viewing this video, we hope that you'll be able to identify regions of the reward pathway and understand the role of the ventral tegmental area and nucleus accumbens with regards to dopamine release, understand the physiological effects of dopamine release in reward processing, and describe the molecular structure and use of heroin. Compare endogenous and synthetic opioids, demonstrate an understanding of the dynamic interaction between opioids and G protein-coupled receptors, as well as address the functional role of long-term potentiation in the dopaminergic pathway, and convey the actions of opioids on GABA interneurons in the ventral tegmental area.